Hello, and welcome to the presentation for software-based monitoring and analysis of a USB host controller subject to electrostatic discharge. My name is Natasha Jarus, and this work is done by me, Antonio Sabatini, Pratik Maheshwari, and Dr. Sahra Sedigh Sarvestani. So I am a PhD candidate in computer engineering at the Missouri University of Science and Technology. My work focuses on modeling and metamodeling complex systems, in particular to understand how to make them more dependable. The research that I'm presenting today has been done in collaboration with Samsung, Ford, and researchers from the Missouri S&T Electromagnetic Compatibility Lab. So today I want to talk to you about the dependability of control systems, in particular when they're exposed to static electricity shocks. So this kind of static electricity discharge can cause a number of different problems, including screen glitches, program crashes, faulty sensor readings, or in the worst case, permanent hardware damage. Therefore, dependable cyber-physical systems need to be robust to these kinds of shocks. While we understand what happens to the hardware of a system when a particular static shock occurs, we have much less insight into how a particular static shock might affect the execution of software on a system. So let me give you a big picture for what is going on with this research. This research started with Samsung's Consumer Electronics department, and they were interested in building more dependable digital cameras and things like that. And we have also been working with Ford on their self-driving cars. They're interested in cars that literally do not crash when exposed to this kind of shock. So you may wonder, how common are these kinds of things? Various devices, welders, things like that might cause this kind of interference, and as well, people can go on the internet and for a moderate sum of money purchase hardware that can produce up to 50 kilovolt electric shocks. So the kinds of things necessary to create these shocks are relatively available to not even nation-state actors. So when a particular shock occurs, this causes a fault in some part of the system, and then the shock itself may propagate through the system and affect other components, or that component may fail and cause a cascading failure of other parts of the system. Nonetheless, the effect is that the fault travels through the system and causes some kind of user-visible behavior, for example, non-functioning brake system. So this is not ideal, and we'd like to be able to prevent this by monitoring these devices via built-in instrumentation. So we take each device, we instrument it, and we monitor how it behaves. And we find anomalies in this system operation, and we can classify these anomalies and then be able to pick out a mitigation strategy for them. Perhaps we can entirely recover from the fault, or at the very least, we'd like to avoid catastrophic failure. There are two common approaches to monitoring ESD on a system. The first, hardware instrumentation, provides a precise understanding of how electrostatic discharge, static electricity shocks, enter and propagate through a system. However, due to the number of hardware probes required, it's difficult to scale up to monitoring complex control systems. As well, the hardware modifications required make this infeasible for field test conditions or for using commercially available equipment. On the other hand, software instrumentation can circumvent several of these problems, but many software instrumentation studies focus on user-visible faults, such as display flicker or program crashes. So these can provide a high-level understanding of when the system is shocked here, it causes a display fault there, but not an understanding of why. On the other hand, lower-level faults, if you're looking for bit flips in registers or incorrectly triggered interrupts, instrumentation for these is usually done with low-level software that requires complete control of the system. And as several studies have found recently, the software executing on a system can affect its immunity to ESD. So ideally, you'd like to be able to run the software that will be run in the field on your system that you're testing to give you a good, accurate approximation of how the system behaves under ESD in field conditions. So the goal of this research is to improve software instrumentation for these low-level faults. we'd like to achieve software fault detection on consumer hardware in field use conditions, so without requiring hardware or significant software modifications. As well, we'd like to enable lightweight, real-time monitoring and failure recovery, so we can understand what the system is doing and in real time decide how to recover from an execution problem. The approach that we're going to present today is generic and can be applied to many different system peripherals. However, we validate and demonstrate it by applying it to USB devices. So our monitoring approach focuses on the USB host controller. This is a device that connects to the USB bus and does USB host device operations. So, for example, this has to do with connecting and disconnecting devices. When you plug a flash drive, a USB peripheral into your USB host, your computer, the host controller is responsible for telling the computer you have a new device attached. It configures power delivery to those devices, and it communicates control and data signals between the CPU's memory and the USB devices on the USB bus. So if you look at the system diagram here, we're primarily interested in the host controller interface. So your client application talks to a USB peripheral driver. The peripheral driver talks to the host controller driver, which then tells the host controller what to do, and the host controller actually sends the communication out on the bus to the USB peripheral. So everything that happens on the USB bus, the host controller can see, which makes it an ideal choice for instrumentation. So the host controller exposes a set of control registers to the host CPU, and this is all we can see about the host controller. The rest of its internal operation is a black box, as far as the host CPU is concerned. So these control registers conform to the Open Host Controller interface specification, so we can understand what their values mean and how they're supposed to operate. We go through and record snapshots of these register values to approximate the host controller's internal operation. So this assumes that certain sequences of values will be common during typical system operation, and hopefully, when exposed to ESD, we'll observe some anomalous values that indicate the host controller is not executing as it normally would. Our goal is to look at these anomalies that we've recorded and infer when the system has been exposed to ESD. So our initial instrumentation approach, these host controller control registers are located in a particular region of physical memory. So we found an open source tool called MyRegRW and modified it to suit our needs. So this hat consists of a system driver that can read those physical memory addresses and a user program that can send control signals to the driver telling it, please read these registers, please write them out here, that sort of thing. So we read the values continuously while exposing the system to ESD. However, these register values seem to remain mostly constant. So we failed to even capture typical host controller operation, much less anomalous operation. So why is that? We measured the sampling rate of MyRegRW and found out that on this system it took snapshots 342 times a second. So the system has a 400 megahertz clock, so in the worst case, the register values for these control registers might change at 400 megahertz, and this gives us an astronomically small chance of actually observing a given value before it changes. Even if we relax some of these worst-case assumptions and improve the performance of MyRegRW, we need 5 orders of magnitude improvement here, which is a bit difficult to achieve. Also, MyRegRW is racing the host controller driver to read values written by the host controller before the driver overwrites them. So, for example, MyRegRW might take a snapshot, an ESD event might occur, the driver runs, because it's triggered by an interrupt or something, overwrites those register values that the host controller had written, and then MyRegRW takes a snapshot again, and misses this entire ESD event because we simply can't observe those register values at the right time. So to fix both of these problems, we took a different approach, where we instrumented the host controller driver itself to record the register values at the start of each function in the driver. So to your right, you can see a snapshot of these register values. So it consists of the function being called, the register names, and the corresponding register value. So each one of these is this entire thing is a register snapshot. This gives us an exact picture of what the driver sees the host controller doing. We take these snapshots before the driver does anything to those registers. It requires minimal modifications to the driver code, simply a call to a logging function. Values are recorded using the kernel logging framework, and the overhead, even with this naive approach, is quite low, 10%, and this could be optimized significantly, provided that it works. So once we're able to capture these snapshots of the register values, we need to analyze them. So our analysis approach consists of running the system normally and capturing so-called baseline logs that establish an idea of how the system behaves while it's not being interfered with, under normal conditions. We also capture ESD exposed logs where we expose the system to ESD and observe its behavior. So each one of these log files consists of sequences of snapshots of register values. So we'll call these log files execution traces, and a snapshot of the register's values, so that entire thing on the previous slide, constitutes one state. So thinking about this as a large state machine that the system is executing, it may be complicated, but nonetheless, each one of these register snapshots constitutes one state in that state machine. So once we have these logs, once we have these traces, we need to turn them into some approximation of a state machine. So initially we take each trace and we find the repeated register snapshots in there and coalesce them into one state per unique register snapshot. And then we repeat this process again to construct a global execution graph, unifying all of our execution graphs for each trace. So this gives us a global context in which we can understand each one of these traces as a path taken through this big state machine. Based on this, we can see what paths and what states are visited by baseline logs and what paths and states are unique to ESD-exposed execution traces. So the case study for this system is a microcontroller running Linux. So this is the Friendly ARM Mini 2440. It has a 400 megahertz ARM CPU made by Samsung. And we attached a flash drive to its USB port and ran a script that copies data to and from the flash drive. So this gives us some activity on the USB bus while we're observing the USB bus's behavior. So we ran this just sitting on a desk and captured some baseline traces, and then we exposed it to ESD and captured ESD traces. So we used two different types of probes for the ESD. So one produces an electric field, just a voltage potential, and with this we injected pulses between 500 volts and 5.5 kilovolts. And the other creates a magnetic field coupling, so this has something along the lines of like a current loop. And with this, we were able to inject pulses between 500 volts and 8 kilovolts. So the system was more immune to the magnetic field coupling, so we were able to go higher with the ESD pulse voltage. We positioned the probes over the USB port or over the USB host controller integrated circuit. So this ideally injects ESD somewhere where we'll actually be able to observe its behavior or its effects on the system, the parts of the system that we have instrumented. We took a look through the data and we found that some of these register values were interesting when the system was exposed to ESD. So the first ones of these is the pair HC interrupt enable and HC interrupt disable. According to the specification, these are supposed to be duplicates of each other. They control whether or not various hardware interrupts on the host controller are enabled or disabled. So baseline data confirmed that this host controller follows the specification, but under ESD exposure, slight dissimilarities are observed. Sometimes bit 7 disagrees between the enable and disable register. Another example of potentially ESD-caused anomalies is in the HC interrupt status register. So this records whether an interrupt has been triggered, and when exposed to ESD, we observe certain interrupts are more likely to be triggered. So in particular, we have frame number counter overflows. So each USB frame is assigned a number, and when a sufficient number of frames have been sent, the frame number counter overflows. So we see that perhaps a lot more frames are sent while ESD, or when the system is exposed to ESD. Another thing we observe is an increase in hub status change events. So this has to do with whether or not the USB hub itself as having devices plugged into it or unplugged, or things like that. The EHC control register also had some interesting results. So this allows the host controller to decide, or the host controller driver to decide what the host controller is going to do next, if it wants to send control signals or if it wants to do some bulk data processing. Under ESD, we observed an increase in control frame processing and a decrease in bulk data processing. We also observed an increased number of new control and data frames, so it's possible that the ESD is disrupting the bus's operation, resulting in more status change frames and more retransmission of corrupted data frames, which would appear to us as fewer or lower data throughput and proportionally more control frame throughput. Finally, the HCRH port status 0 register reports the status of the port that we had plugged our USB flash drive into. So this tells you, whether or not a device is attached, the power draw of it, things like that. So values where the port status remains unchanged occur less often, and port enable and disable events occur more often. As well, port resets are only observed in ESD-exposed traces. So these are situations where not just the device on the port, but the port itself needs to be turned off and turned back on again. As well, we observed some anomalies in our execution graphs. So to your right, you can see the unified execution graph of two traces, one a baseline trace and one an ESD-exposed trace. The green states appear in a baseline trace somewhere. Red states are unique to ESD-exposed traces. So in this execution graph, we can see several potential effects of ESD. So one of these is transitions from baseline states to non-baseline states. This may be caused by the host controller driver automatically recovering from an error or something along those lines, and we only see that error recovery state when we've actually exposed it to ESD, or it might be something else. We also see transitions between non-baseline states, and furthermore, transitions between baseline states that are not present in baseline traces. So while both these states appear in a baseline trace somewhere, they don't make sense, or we haven't observed them in baseline traces consecutively. So this may be a case of a bit being flipped, but it's flipped to another valid value, or some other type of, maybe we're taking a different path through the control. Maybe an if statement gets taken that's different, or something along those lines, through the driver. And then finally, we observe transitions from non-baseline states to baseline states, so this may be, in particular, indicative of the system recovering itself. But nonetheless, these are all different examples of behavior that we see that might indicate ESD execution anomalies. We also observe differences in the distribution of state occurrences between baseline and ESD-exposed traces. So if we think about how a system works, during normal operation, we would expect to see a large group of states that get revisited frequently. So you think about your main control loop, right? These states are going to happen over and over and over again, and they'll constitute a fairly large chunk of the time that the host controller spends executing. And then we'll also see a short tail of exceptional states that handle unusual events, when a device gets plugged in or unplugged, or something along those lines. When the system's exposed to ESD, however, we expect to see proportionally less time spent in those commonly visited states, so a fewer common states, and a much longer tail of unusual or anomalous states. And so when we actually plot this out and we order our states by order of decreasing occurrences, we see to the left you have the blue line shows baseline trace distribution, and there is in fact a chunk of states that get visited relatively frequently, and then a short tail of exceptional states. The red dashed line shows the distribution from our ESD-exposed traces, and again this shows a decrease in those fewer very common states and a very long tail of unusual or anomalous states. We actually cut this graph off. It goes on about twice as long as it does, that little red line, but it doesn't fit on the slide that way. So again, we see some significant differences in behavior between our baseline traces and our ESD-exposed traces. So overall, we've developed a methodology for studying the effects of ESD on system peripherals using software instrumentation. So this works by recording traces of the peripheral's control registers, which we use as an approximation for what the peripheral is actually doing. Its internal behavior. So this internal behavior is often unobservable, but we can see what the host CPU sees, and that in particular can control what happens with the software executing on the host CPU. So this implementation is low overhead and can coexist with any other software running on the system. This is just a modification to the driver, so anything that's running on the system can still use the driver just as it usually would. We were able to observe differences in system operation when the system was exposed to ESD, so it seems like this approach does actually work. So from here, we would like to be able to predict, based on the operation of the system, whether or not it's experienced the effects of ESD. To reverse the relationship, instead of saying this trace was exposed to ESD, is it different? We say this trace is different, so it's probably exposed to ESD. So this could allow us to identify which components on a system have experienced ESD and might require repair or better shielding, particularly if you've instrumented a number of peripherals. And we might be able to determine that an ESD event has occurred automatically using software, and to recover from those resulting errors, which would allow the system to operate in hostile environments at the cost of reduced performance. So we've done some of this work and determined that a naive classification approach can detect ESD events in a system execution trace with 88% accuracy. So this work is to appear in IEEE transactions on electromagnetic compatibility, so keep an eye out for it there. Future work from here, we would like to expand this approach to other peripherals so we can monitor the entire system for ESD effects. We'd like to characterize the effects of ESD at specific injection locations, so we can see a particular, if we shock the board at this particular place, then we see this particular kind of error or this particular behavior, so we can better identify what's happening on the hardware based on what we can see with the software. And we'd like to be able to develop software that anticipates and recovers from these ESD events, perhaps by rolling back to a known good state, or in worst case, resetting some of the hardware so that it can recover. So thank you for listening to my talk.